All right, today we are looking at velocity and acceleration. So we're also going to be looking a little bit more at position time graph and velocity time graphs. Okay, and then we're going to be able to describe motion and calculate acceleration with a new equation that we're going to learn today. Okay, so we have a question to answer before we get going here. Explain how an object can have an average speed but a velocity of 0. Okay, so something to think about here. Think about displacement of the person running a lap around a track. So that should be kind of a hint there. How far did they move from their starting point? So we're going to try to use academic vocabulary such as distance, speed, and displacement in the response. So I'm not going to write my entire response, I'll just kind of talk about it here. So if we think of the example of a runner going around a track, okay, it's a pretty terrible track here. All right, so if we think about a runner going around a track here, let's just call this oval the track. Okay, the runner begins, let's say the runner starts here, like on a normal track, goes around and back to there. Well, our actual equation for velocity is displacement over time. So what is the runner's displacement if they go all the way around and back to the start? Okay, well, displacement is how far you are from the start. So if I went around once and I'm here, I'm back at the start. Well, that means my displacement is going to be 0 meters over whatever time. So our velocity would be 0 meters per second. Now, if we were considering speed, remember speed is just distance over time. So how far did we go? Let's say this is a 400-meter track, so we went 400 meters over however long it took us to get there. So this is why velocity and average speed are different. You can have a 0 velocity and you can have an average speed because velocity involves displacement. Okay? So let's move on here. So discussing motion a little bit more again. Okay, so when we talk about things that are in motion, we're going to draw vectors to describe that motion. Okay, so this would be a motion diagram, and a basic motion diagram is like a picture or a snapshot of equal time intervals. So we could say that this is 1 second, 2 seconds, 3 seconds, and then 4 seconds. Okay, so the picture is taken every second, so consistent time intervals, and then we can use the change in position to describe the motion of the person. Okay, and an easier way to do that is just to look at vectors. Okay, so this is the particle diagram, this is the vector diagram. So these vectors you can kind of see from one to the next, they are getting longer. So what can I say about this person's motion? Is the jogger speeding up or is the jogger slowing down? Well, considering we're covering more distance with the same amount of time, then we're going to be speeding up. Okay, or increasing speed for this guy right here. So if we look at this one, so now we start with this big distance in 1 second, and then we can kind of look what's happening here from the next second to the next second. So we're slowing down here because our distance is decreasing from one person, or from one picture to the next. Okay, so that would be a motion diagram or a picture diagram, and this is my vector diagram, and this is my particle diagram. Okay, this is vector, and then this is particle. So these are three different ways, and we can call this just a regular motion diagram or picture diagram maybe. So we have these three different ways to show motion happening. We have to consider when we're looking at acceleration. We need to know the direction of both the velocity and acceleration vectors to determine if it's speeding up or slowing down. So these ones are pretty easy to determine. Velocity vectors for both of these because they're moving in that direction. Now acceleration vectors, that's a little bit different. So we draw that like this, so acceleration vector, and this one would be about like that. Okay, so the idea behind the acceleration vector is if I take this, let's say it kind of lines up with that. Every time I go from 1 second to the next, it's going to add this on to that first one. Okay, so if I look at this vector plus that one, it should equal this second vector. And then if I add this again, then it should equal the third vector, right? So if I look at my third vector, this chunk right here should equal that vector. Okay, so every second or every time interval, this is just going to get this much faster. So that's the acceleration vector. Okay, if we take this and kind of go to this one we said was slowing down, so it's going to be decreasing by this much every time. So if I look at this chunk in red here, then that should match my next second there. And as we go down, that's going to match that. So it's going to be decreasing by this much about every time. So really this vector could be going, it should be going that way, because I'm going to be taking that much off each time. Okay, so that's how acceleration vectors work with these types of problems. Let's look at a couple examples here. How can we describe vehicles' motion in the diagram below? So looking at our picture diagram here with our vectors, so acceleration and velocity are in the same direction. That means that this acceleration vector will add with a velocity vector each time. Now that's not to scale, that just shows that they're both going in the same direction. So if I look here, particle diagram, vector diagram, if I compare this little chunk to this one, okay, so each time we're going to be getting that much faster, just like we talked about above. Okay, so that's going to be adding to that one, it's going to be adding to the previous one, adding to the previous one, and that would show us how much we're accelerating. Okay, this next one, velocity and acceleration are in the opposite direction, so that means we will be slowing down. So maybe we're coming to a stop. So that's like the one up over here where we're slowing down. Now this third scenario is a little bit different because acceleration and velocity are both going backwards. Okay, so that means I start from a different point and I am going away, or I start from my stopping point, I suppose, I'm going away from that. So the vectors would look like this. I begin on the opposite end and I'm working away from my starting point. Okay, they're both in the negative because I'm going away from that starting point. Okay, so looking again at position time graphs like we did in the last lesson. Okay, we want to find average velocity with this position time graph, and then we want to find average speed. Okay, so we want to find that, and we want to find that. So we're starting here. So this would be like the starting point. We're starting at 50 meters, and we're ending at here, which would be 0 meters. Okay, so this is like that last example we looked at with the car. We're kind of going back to where we started. Now, we can't determine acceleration with this one. Well, we can, but we're not going to talk about that for this lesson. Okay, so we want to find average velocity and average speed. So velocity is a vector, so that has a direction. Okay, so this can be positive or negative. Speed is not a vector, so speed will just be always like a positive number. Okay, so in order to figure out velocity or speed, we have to figure out the slope of this line. Okay, and we could say we change from here to here, here to here, here to here, whatever. It's your choice. Okay, I usually use the beginning point and ending point because it's a constant slope. So we are starting at 50 meters. So we can turn this into a coordinate system. So time is always x and position is always y. So we are at 0, 50. And we finish out at 25, 0. So this is just like any algebra class that you've taken. How do we find the slope of this line? If we have these 2 points, we do y2 minus y1 over x2 minus x1, which is just negative 50 over 25, or a negative 2. So that is my velocity, negative 2 meters per second. So average velocity is negative 2 meters per second, and we can use that information to get average speed. Speed is not a vector, so speed is just 2 meters per second. So that would be those two. Okay, speed does not have a sign with it. It's just how fast is the object going. Alrighty. So we did this example in the last lesson. Okay, so I'm not going to spend a whole lot of time on those. What I want to do is find the velocity of Juanita and the velocity of Heather. How fast are they going? Let's find speed of Juanita and speed of Heather. Okay, so pause the video, see if you can figure that out, and we'll come back to it. All right, so looking at Juanita first. So we start at 0, 0. That's an easy point. And we finish at 6 kilometers. And we'll say, so we go 1.1, 2, 3, so let's say 1.25. Okay, so 1.25 seconds, and we went 6 kilometers. Let's look at Heather. So Heather starts at 0 seconds, but she's starting ahead. Oh, sorry. So let's look at Heather. Heather started later. She started at 0.1 second, but started from the beginning point, so it's 0.10. And where did we finish up at? So let's just say we're all the way out there. So 2 seconds later, or 2 hours later, excuse me, we are at 6 kilometers. Okay, so let's find those speeds. So let's do Juanita first. So we went 6 kilometers from 0. So it's final minus initial, or y2 minus y1. And then it took us, so x2, 1.25, or x1. So we went 6 kilometers in 1.25 hours. Don't overcomplicate this. This is slope formula, but let's say how far did we go from the beginning and how long did it take us? So we went 6 kilometers in 1.25 hours. We divide that out, 6 divided by 1.25, and you get 4.8. And this is not meters per second, this is kilometers per hour, just because of the units that we have on this problem. Okay? Let's move that down so we can see those. So we have kilometers in the vertical axis and hours in the horizontal axis. Okay, so that is Juanita's speed or velocity. And if we wanted to make it a vector, we could say positive, and speed would just be 4.8 meters per second. Okay, Heather, now we have to do Heather's speed and velocity. So she went 6 kilometers, that's y2, from 0 kilometers, y1, over, so we do y2, so 2 hours, minus 0.1 hours. So she started 0.1 hours later. Okay, so 6 kilometers, and that would be 1.9 hours. So 6 divided by 1.9 gives us 3.16. And that is kilometers an hour again. Okay, so positive 3.16 kilometers an hour. Just find the slope of the line. And speed would just be 3.16 kilometers an hour. Okay, so we found velocities and speeds using this graph. Okay, so let's step it up, and we're going to be looking at velocity time graphs. All right, so we have the velocity time graph here, and once again, time is on the x-axis. And now, rather than position, we have velocity on the y-axis. So we have to kind of change our brain a little bit here so we can figure out velocities from this graph. So here, we have velocity on the y-axis. So at 1 second, we're going 5 meters per second. At 2 seconds, we're going 10 meters per second. At 3 seconds, we're going 15 meters per second, okay? So we can just determine at what time we're at and how fast we're going. Okay, so we can use this, again, the slope of this line is going to give us acceleration, right? So we are seeing the change in velocity. So a change in velocity is acceleration. So with this one, we can it's easy enough just to count up and over because we're going up 5 over 1, up 5 over 1. So it's 5 meters per second, and that is the change, so it's 5 meters per second squared is our acceleration. Okay, so it's pretty simple, just like the last one, but you have to pay attention to what the axes are. We're doing velocity and time, so that would tell us that this is going to give us acceleration if we find the slope. It's change in velocity over change in time. Okay. So if we're looking kind of like we did before at motion diagrams, so looking at this GIF here, how would I determine which car has the greatest acceleration? Or how can we describe the motion of these cars? Specifically, we're looking at the red car, okay? So think about the red car, what's happening. Okay, let's keep our attention here. So it kind of starts fast and then slows down as we get towards the end. All right, so maybe when we take this snapshot, the red car is going the fastest, but then he's slowing down. So his acceleration, or that car's acceleration, is decreasing. Okay, so that the motion is getting slower, so our acceleration is decreasing, so we call that a deceleration. That is the negative acceleration. Now if we look at the other cars, just because we want to, green car, kind of follow it. So he starts kind of slow, and then he just kind of keeps going. So it looks like he kind of gets to a constant speed, maybe right about in here. And then, so he's kind of accelerating until we get to here. The blue one, though, the blue one is accelerating because he kind of starts slow, but then he starts going faster. Okay, so just kind of using diagrams to describe motion here. All right, so the rate at which velocity changes, as we discussed in the last one, is called the acceleration. All right, so we could draw graphs for that. We can look at motion diagrams for that. Whatever works, okay? If we were to say, let's say the blue one here, we could kind of draw a graph for that. I would say that the acceleration for the blue one is fairly constant. And then if we drew the acceleration for the green one, so he's speeding up, and then he's just kind of leveling off and maintaining the same speed. That would be what I would draw for the green one. And then the red one's pretty fast. Maybe he's accelerating pretty quick for the most part. And then I would say he starts to slow down. So this might be what I draw for the red car. Okay. This one is probably the hardest to draw for a velocity time graph, just because he's speeding up maintaining for a second and then slowing down. But if you think about that, velocity is fast, and then velocity is the same for a second, and then the velocity is decreasing because everybody's passing me. All right? So that would be how I draw a velocity time graph for those three. Okay, so now we're going to try to look at the equation for acceleration. So acceleration is rate of change of velocity. Okay, so we have delta V. So acceleration, if we break it apart as much as we can, it's final velocity minus initial velocity over that time. All right, an easier way to write it, acceleration equals delta V over t. So change in velocity over time, and change in velocity breaks down to final minus initial velocity. Okay, our unit for acceleration, I wrote this once already, is meters per second squared, because we're finding change in velocity, which velocity here is meters per second over time, which is usually in seconds, so it's meters per second, which gives us meters per second squared. Okay, another thing to think about, velocity is a vector, or excuse me, acceleration is a vector, so we have to have a direction. So is it increasing going forward, or is it decreasing or slowing down? Okay, and what are some other ways we can write this formula? So we're looking at solving the formula a few different ways. So let's write it out. Let's say we want to solve for time, okay? So how would I get the time out of the bottom? Multiply both sides by t, all right, and that would get rid of it there. And then I would have to divide both sides by a, and that would get rid of my a on the left. So if I were solving for time, I would have final velocity minus initial velocity, or delta v, over acceleration. Okay, not too bad. So if we were to solve for final velocity, that's one that we kind of have to do every once in a while. All right, so solve for final velocity here. Let's get rid of this stuff off to the right. All right, if I want to solve for that one right there, I have to first get rid of my time variable, right? So that gets rid of it there. I have AT equals VF minus VI, and now I'm solving for this one, so I have to add both VI to both sides there. Oops. All right, and that will get rid of it here. So I would have AT plus VI equals VF. So final velocity equals initial velocity plus acceleration times time. If I were to solve for final velocity, that would be how I do it. Now, normally I just use the basic equation, acceleration equals change in velocity over time, and then I just work through it as I need to. Rather than remembering a bunch of different equations, it might be easier just to use this and plug everything in as you need. So just like we solved for in the last equation, we can also write our acceleration equation this way, but like I said, I like to just keep it this way and go from there. Okay, if you want to have this equation down, you can. Okay, but this might be easier if we're trying to find a final velocity, and that equation might be given to you if you need it. Okay, so let's try some problems here. So we've talked about this already. We're going to jump in. So a truck's speed increases uniformly from 5 meters per second to 15 meters per second in 20 seconds. Determine the acceleration. So uniform, that just means it's a constant acceleration. All the problems that we'll be doing here will be uniform acceleration, so there's no change, and we'd have to calculate 4 or 5 different accelerations. It's just going to be one acceleration, okay? So let's label these things. So we're going from 5 meters per second. So that is my initial velocity to 15 meters per second. So we're going from 5 to 15. That's the final velocity. And our time that it takes us to get there is 20 seconds. Okay, so we have everything we need to find acceleration. Acceleration is final minus initial over time. Let's just plug everything in and we can find acceleration. All right, so it's 15 minus 5 over 20. So 15 minus 5 is 10 over 20. That gives us 1/2. And I would like you to write it as a decimal, so it's 0.5 meters per second squared. Okay, so we're increasing at a rate of 0.5 meters per second squared. So every second, I'll be going 1/2 a meter per second faster. Okay, let's look at another one. So a bus moving at a speed of 20 meters per second begins to slow. So we have to pay attention to the wording here. So we're given a bus is moving at a speed of 20 meters per second. This is my initial velocity. So let's write that down. So 20 meters per second begins to slow, and I have that in red. Slow means it's going to be a deceleration or a negative when we get the answer. Okay, slow at a constant rate of 3.0 meters per second squared. So this per second squared is going to tip me off that this is an acceleration. Okay, and since it's slowing down, that means this needs to be negative. Okay, so we have an acceleration or a deceleration here of negative 3.0 meters per second squared. Okay, so the last part, how long before it stops? So here's another key word for these kind of problems. If it stops, what is the final velocity? Okay, well we know that if something stops, that it's not moving. So final velocity is going to be 0 meters per second. Now we have 1, 2, 3 pieces here that we can plug into our acceleration equation. And we're looking for time. As it says, how long does it take to stop? Well, we have the pieces that we need to find that time. Okay, so let's plug them all in. Negative 3.0 meters per second squared. Final velocity is 0. Initial velocity, we were going 20 meters per second. And our time, we don't know. Okay, so this is some algebra. It's not too terrible. So 0 minus 20, that's negative 20 meters per second over time equals negative 3.0 meters per second squared. All right, so how do we solve this? We did our quick subtraction there. Now we're solving for time, so that means we have to get this out of the bottom. You can never solve for a variable when it's in the denominator. Multiply both sides by t, and that's gone. So I'd have negative 3.0 meters per second squared times time. So I'm going to have to divide by that negative 3.0 on both sides. So we do negative 20 divided by negative 3, and we get a time of 6.67 seconds. And if you wanted to, just like in all your math problems that you've ever done, you can take all your variables, plug them in to see if it works, which it should. Okay, so that's how we solve an acceleration problem or a deceleration problem.